For more information, please visit SGMAK Associates website.
In this module, I'm going to explain a few problems on test of hypothesis. I'll discuss one problem that's a two-sided test and one problem that's one-sided test. This is a test on a single parameter. Both of them are tests on single mean. Setting up hypothesis comes from problem statement. And the first problem that we are looking at is a two-sided test. You can think about you want to keep a process on target at mean equal 50. Hypothesis test is always about parameters. So null hypothesis is mu equal 50 and alternate hypothesis mu not equal 50. I want to keep the process on target at 50 and any shift from the target is I'm concerned about and I want to detect. Now there's no reason given here, but if you look at the inputs here, process standard deviation is supposed to be known at 2.5. So I have some knowledge about the process and I'm testing on the mean only. I'm using a sample size of 10. So right now we are arbitrarily setting up. This can be designed later on. There's one example given where we have designed the sample size. So we work with the sample average to draw inference about the parameter. Another input needed is level of significance for the test, and which is set at 5%. The standard notation is alpha, so alpha is 0.05. Now the test will be done in three different ways. One is based on acceptance region, then we'll do based on p-value, and the third one is based on confidence interval. And we'll show basically the three different ways to test hypothesis. All will lead to the same results if you have done them correctly. So what you see here is an acceptance region, two-sided test. We got these two bars. In between region is accept the null hypothesis. The correct word is fail to reject. And on the other two region, it shows reject the null hypothesis. What you're plotting on this curve is a sample average, or how to compute those bounds. So on one side, your bound is 58.45, and on the other side, the bound is 51.55. So the equation is mu plus minus z alpha over 2 sigma over square root of n. Our sample size is n. Sigma over square root of n is used because we are looking at standard deviation of sample average. So based on a sample size of 10, value of sigma and alpha 5%, your acceptance region or fail to reject region falls between 48.45 and 51.55. Now your observed data is 52.5, so which falls in the reject null region. So in this case, based on the data, we're going to reject the null hypothesis. Reject null in favor of the alternate. So process is not on target at mu equal 50. That's what we can conclude based on the data given. Now since we're working with limited data, we make two types of error in testing hypothesis. When reject null hypothesis, given null is true, we make type 1 error. We accept null hypothesis and null is false, that's type 2 error. So we make these two types of error. We can't avoid making them because we're working with limited sample, but we try to minimize them and design sample size accordingly. So the notation for type 1 and type 2 error are alpha and beta. That's the standard notation used in the books. So I made a probability statement. If alpha is if I get a sample average less than 48.45 or greater than 51.55 given the mu is 50. That's when I reject the null, even when it. So moving on. So we looked at based on a acceptance region. If you look at the concept of p-value, p-value is for a two-sided test is given by this expression shown 2 times 1 minus phi of z observed. Z0, suffix 0, you're converting the observed data, observed sample average to the corresponding z-score. So z observed is x0 minus mu divided by sigma over square root of n. That number comes out to be 3.16. For a two-sided test, so p-value is given by 2 minus phi of 3.16. We take absolute value of z observed, and that number comes out to be a low value, 0.002. So p-value for this test is 0.002, which is less than alpha, set at 0.05. So when you get such a low value, low p-value, less than alpha, we reject the null hypothesis. P-value less equal alpha, we reject the null. That's the rule. So in this case, we're rejecting the null hypothesis in favor of alternate hypothesis. So this is the second method of solving the same problem. Now if you go to a two-sided confidence interval, since alpha is 0.05, we got to set up 100 times 1 minus alpha. So it comes out to be 95%. So for alpha 0.05 corresponding, we got to work with 95% confidence interval for mu, and we got to work with two-sided confidence interval. The expression is shown next. This x bar observed plus minus z alpha over 2 times sigma over square root of n. X bar observed is 52.5, so we get a confidence interval which is between 50.95 and 54.05. Ends are included. Moving on. So in the previous example, since the confidence interval does not include mu equal 50, confidence interval does not include the hypothesized value mu equal 50, so we're going to reject the null hypothesis. So all three methods give us the same solution. Now, here's one example where you estimate sample size. In our example, sample size of 10 was taken arbitrarily. Now, we design sample size by combining type 1, type 2 error, and in type 2 error, we want to specify the amount of shift. So now we are solving for sample size for this two-sided test. Sigma is 0.25. We are talking about a shift of 1 unit, and we want to detect it 90% of the time because corresponding beta error is 0.10. Our type 1 error is 0.05. So using the expression here, you can retrieve from any stat book. We will not go into the derivation for that. Here, n is given sigma squared times z alpha over 2 plus z beta in a bracket squared divided by delta squared. Delta is the amount of shift. And that number comes out to be 66. Remember, we arbitrarily picked up a sample size of 10, but we need a larger sample size of 66 if you want to control type 1 and type 2 error. Type 2 error for the amount of shift we are interested in. Sample size is 66. Now another example. When you're setting up two-sided test, it's not an issue. You look for setting up for a target and you can set it up. This is a two-sided test. Some problem gives you one-sided hypothesis. I think I've explained that in another module. And so here's an example. Um, I want to use bottle to fill in with soda, and the bottle must withstand more than 150 psi for safety reasons. So the question is, which formulation is correct? Null mu less equal 150, alternate mu greater than 150, or the alternate is mu less equal 150 and null is complement. So I think the key thing is what I'm saying, that the formulation I've shown here, mu less equal 150 null and alternate mu greater than 150 is the right formulation, because in this example the type 1 error represents, if you make a type 1 error in this formulation, then you are accepting defective material as good, which is more serious error compared to the other formulation. So that's the right formulation. Now I show quickly another example with a one-sided test. So in this case, mu is less equal, null is mu 40 or less, alternate is mu greater than 40. This is one-sided. Sigma is given as 1.25. We're using sample size of 10, 5% type 1 error, and we have a sample average of 40.5. So in this case, the critical region is only as one bound, which is shown as the bound for reject null hypothesis region, which is given by mu 0 plus z alpha sigma over square root of n. Whole alpha gets added here because it's one-sided test, and that number is 40.65. Since our sample average happens to be less than 40.65, we fail to reject the null hypothesis. It falls in the fail to reject null region, so we fail to reject the null hypothesis. If you compute the p-value, which is given by, for a one-sided test, 1 minus phi of z observed, and that number comes out to be 0.104 or 10%. Alpha is 5% or 0.05. Since p-value is greater than alpha, we fail to reject the null hypothesis. See, the rule is if p-value is less equal alpha, we reject the null. Otherwise, we fail to reject the null. Now here's another approach, third one, confidence interval. Just you have to be careful because it's a one-sided test. You got to set up one-sided confidence interval, and you look at the alternate hypothesis. This alternate says mu is greater than 40. So you got to pick up the appropriate confidence interval. We select the lower bound confidence interval, and lower bound says mu has to be greater or equal x bar minus z alpha sigma over square root of n. So based on available data, mu comes out to be greater or equal 39.85, which is not consistent with our alternate hypothesis, mu is greater than 40. So data based on confidence interval does not support alternate hypothesis. So our conclusion is we fail to reject the null. So we say there is no reason to reject null based on the data provided. To complete this module, we estimate the type 2 error. And type 2 error estimating, we got to specify the new mean that you're interested in, shift to 42. So we are trying to find out what kind of error will make. Error means you are not able to detect the shift if it shifts to 42. So in terms of process, you can think about process is operating at 40, and what kind of error you make of not detecting a shift mu equal to 42. So we go with the basic definition. What's the probability of accepting a hypothesis? Well, mu is 42, and that expression is shown if you get a sample average less than 40.65, given mu equal 42, we make the type 2 error, and that comes out to very small, 0.0003. So there's a very small type 2 error in this case, so we'll be detecting a shift to 42 easily in this, even the sample size of 10. And that's what it shows. So this module shows you 3 ways of solving a hypothesis testing problem, an example of how to compute the sample size, combining both type 1 and type 2 error, and how to estimate a type 2 error. Okay, hopefully this will be of use to you. Thank you.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.